So first question A, where is Fourier transform useful? Important primary use of Fourier transform. Can you put that into words? There is a, okay, screen share now. There is a 2-word answer for this. But even otherwise, I try to answer this in 4 or 5 words. According to you, where is Fourier transform used? Okay, or let me also put it this way: primary use of or sinusoidal representation. Sinusoidal or oscillating sinusoidal representations. Analyzing signal frequency component is one thing. Okay, you can split it into frequency components. Okay, so that's partly correct. Okay, my answer would be frequency response. Characterizing, analyzing, okay, frequency response. That is whenever you have like things are periodic repeating, AC circuits, you can characterize signal. Okay, one is you can characterize signal. You can see what frequency are there. That is one thing. Characterize signal. Second is you can also characterize. Characterize is like you can quantify. Characterize input and output relationship. Characterize input and output relation. Okay. So let me give you a very simple example. Okay, this is a minimum working example. Now your input is this. Input, let's say, is input x of t is cos, let's say 10t minus 50 degrees. Okay, then you have your system transfer function. This is h of s, let's say 1 by plus, let's say 1 by s plus 5. Question is, we're saying you can characterize relationship between input and output. Characterize output y of t. Put y of t. Again, before we plug in numbers, can you put this into simple words like what do you expect of y of t right now? I have 2 specific questions. So, what do you think of y of t? Describe y of t based on what I have given. Describe y of t. Okay, and then the second one is, so how would you get y of t? 2 questions. Okay, Madhurima, exponential signal, fine. Yeah, in fact, these are the basic, uh, subtle details that I wanted to first sort out. Is this exponential? See, again, when things are put into this form, right, abstract form, when I say, this is, you can characterize frequency response input output, doesn't make sense. But at least, if you take a simple example like this, look at it, things make better sense. Okay, so this is not going to be exponential. So what we are asking for is your system of S, and you have input as cos 10t minus 50 degree. Okay, what would be your output? Cos 10t minus 50 will be your output. Someone else try. For example, in a AC circuit, you got your, voltage is this. It passes through a system as a resistor or something like that. And then what is your output? Yeah, but Mondrimo notice e power minus 5t into 10t. But notice in cos 10t, cos itself is a function of time. No, it's going to be different. Okay. Someone else try. And notice, so one point is when you say frequency response, this is going to be steady state. After a long time, system stabilizes. Okay, if it stabilizes, what is going on in the system? Okay. Again, when we say this, technically what we should do was, okay, at steady state. This is kind of implied. Okay, they don't have to explicitly give this steady state. Anyone else? So this is where we have the first word, C. Okay, this stands for sinusoidal input. Sinusoidal input. So here your input is sinusoidal. Your output is also going to be sinusoidal. It is going to be sinusoidal. So that raises a couple of questions. So it has to be, write down things that could possibly change. It has to be, cos t. Should it have the same amplitude as the input signal? That's the first question. No, it can have a different amplitude. That the purpose of this system is to change the amplitude. Either there can be a gain greater than 1 or attenuation less than 1. Right? The system can change the amplitude of the signal, input signal. So for the input, the amplitude is 1. Whatever the amplitude is, again, it kind of gets scaled accordingly. Okay, so notice the amplitude there is 1. Okay, 1 cos t 50 degree. The amplitude here can be different. Okay, h of s characterizes that, and then can the frequency change? What can be the frequency here? Can you guess omega? Frequency doesn't change. This is a important assumption in linearity. There is no, one frequency doesn't affect the other. This is going to be same 10 as that, but the phase will change. The phase will change. It doesn't have to be 50 degree. Again, both this change, what is going on to the amplitude, what is going on to the phase, we have kind of partly seen this in impedance, right? H of s quantifies that, or characterizes that, how much A is going to change, how much phi is going to change. Okay, and at the end of the day, as far as you give something sinusoidal, you are going to get something sinusoidal out of it. The frequency cannot change. Things are linear. Okay, non-linear things, it could be slightly different, but things are linear. Frequency doesn't change, and it has to be this. This is referred to as sinusoidal input, sinusoidal output. So input is x of t is cos 10t minus 50 degree. Transfer function is given. Again, when they ask you for a output, typically they are asking you for steady state response. Even though it's y of t, okay, what is the amplitude of y of t? And then what is the phase of y of t? Both are quantified in h of s. Let's do this example here. Okay, where does this show up? Shows up at many places. This will show up in AC circuits is one thing. Notice in viscoelasticity, type of experiment is doing oscillatory shear experiments, right? The strain and stress need not be, uh, can have a phase lag. The amplitude can also change. Okay, so let me elasticity. Okay, um, oscillatory shear. Stress and strain or oscillatory. You could also, there are many other places this is generally applicable. Okay, so the first question is means the transfer function will just affect the phase in sinusoidal input. It is affecting two things. One is becoming A, this amplitude 1 that is becoming A, and then minus 50 becomes phi. It's affecting phase and amplitude, two things. You put a here, the amplitude here is 1. So technically what happens is, have input technically has a put amplitude. Okay, it will also have a phase. So let me write it as xi ei. This goes through a system that has a transfer function. No, this is at a specific frequency. Okay, at omega specific frequency. This goes through a system with transfer function h of s. Okay, so at that omega, this will have a amplitude of h omega and an angle of phi omega. The transfer function will have a phase and amplitude. Okay, And your y again will be, this is your y output that will have a phase, amplitude and phase. And notice, so according to this arrow, this y should be technically equal to the input. It gets changed by the gain here. Okay, and take the angle phi. Phi w gets added to that. Whatever the phase change at omega, that gets added to it. So there is a phase change, there is an amplitude change. So this is, notice this is your gain. Amplitude change, and there is a phase change. That is I have just rewritten h of s this way. It has at any frequency it will have a amplitude and phase. Okay, impedance is a simple example. Okay. At omega, this will be h omega with a phi omega. And again, what is not explicitly stated is, so frequency response, you are bothered about steady state. When they say frequency response, this implies you're talking about steady state. There will be initial transients, but in frequency response, all you care is, hey, what is the change in my input amplitude? What is the change in phase? Does it make sense? In fact, I will also show an example where, okay, what do you mean by steady state? What do we mean by, transients? I'll give an example here. So let's take our example. H of t is 1 by s plus phi. X of t is cos nt minus 50 degree. So your x of t is cos of, AC circuits. Filters is also one more important example. Let me write filters. This is cos of 10t minus 50 degrees. H of s is 1 by s plus phi. Okay, so your h of j omega is 1 by j omega plus phi. Okay. And what is our omega? Omega, this is few details over here. Notice omega equals 10 per second. Okay, and this is phase is minus 50 degree. That is fine. And now your y of t, let's also write down this as amplitude and phase value. What is the amplitude of this? What is the phase of this? So this has an amplitude of 1 by square root of omega square plus phi square. And then you have tan inverse of, there will be negative sign because this is in the denominator. This is tan inverse of 0, that disappears. If you want me to write this clearly, let me write this. H of j omega. Okay, if I write it as an amplitude and a phase, okay, this is going to be the amplitude of that is omega square plus phi square. The phase of that would be phase of the numerator minus phase of the denominator. Phase of the numerator tan inverse 0 by 1. Imaginary part is 0. And then this is negative tan inverse omega by 5. Okay. See, this is what I showed here. Notice. So at a given omega, this function is essentially, it has a gain and it has a phase change. Impedance is a simple example for this. But this is more general than impedance. Any circuit, typically any linear circuit, this is useful. Okay. So can you quantify this at 10 radians per second, at 10 rad per second? Your, what is the amplitude of H? And then what is your P? This omega is in radians, so you can substitute it directly. This is minus tan inverse of 10 by 5. What are these two values? And some of you might be wondering what it is. I just put, steady state S is j omega. This, notice if you take e power minus j e power minus st, that would be e power minus sigma minus j omega t, right? Any transient part, sigma, you set that to 0. So any transient part, you set that to 0. In fact, you can write this as e power minus sigma t into e power minus j omega t, right? So when t is very, very large, okay, you don't really, you don't bother about this term at all. You are bothered about, okay, what is this term doing on? Okay, so you're setting s as j omega. Now, what is the value of at this 10 rads per second? What is the value of this amplitude of H and amplitude of phase of H? I have to do this. So this is square 125 root of 125 1 divided by answer. Yeah, amplitude becomes 0. So now this depends on frequency. This becomes, that's correct. I also got 0.089. So the gain is actually the purpose of the system is at this frequency, it's going to really attenuate whatever comes in. If one comes in, one becomes 0.089. Right? There is a lot of attenuation happening at 10 radians per second. Attenuation is things getting smaller. Okay. Let me also I'll show this pictorial in a moment. What is a phase? This is tan inverse of 2. Okay, my calculator is not working. Like the battery is dead. Gate calculator. Ooh, tan inverse 63, and that's correct. That this is minus 63.4543. Okay, 43, and what is this? This is in degrees. So your output y is going to be the input amplitude multiplied by h. Sorry, multiply by h. That specifically is input amplitude is 1. The gain that is going on here is 0.089. Okay, so you get the amplitude of the 0.089. And what is the angle of y? That is going to be, take the input angle. How did I put that? Pi. The angle of h gets added to this. Okay, and that would be minus 50 degrees minus 63.43 degrees. How much is this? Getting minus 113.43 degrees. So what this means is your input goes to a system with a transfer function h of s, and what you get is the output. Your input look like this. Your input was something like this, and it had a 50-degree phase. Let's say this is 0 phase. It had a phase of 50 degrees. And its amplitude was 1. This was your signal. The output, on the other hand, with respect to, let's say, 0 phase, your output is now minus 113 degrees. And this is like now really attenuated. Okay. Steady state. So this keeps on oscillating like this. I'm just showing like one period. This amplitude is now 0.089, and then this phase any t equals 0, let's say this is t equals 0 phase, right? That is going to be minus 113.63 degrees. So this is sinusoidal input, sinusoidal input. This is sinusoidal. So this is what we mean by frequency response. So at a given frequency, what happens? If you change the frequency, how this attenuation happens? If 1 becomes 0.089, 100 becomes 8.9. These are linear systems. So if you change the input, scale the input, output gets scaled and all of that. If you change the frequency, how this changes also changes. That is characterized by H of S. If you put a different frequency, you will get a different amplitude and phase for the transfer function. Okay. So this is the primary use of Fourier transform for sinusoidal representations. You can do frequency response. If you can study one frequency at a time, right, or at least given problem typically has certain frequencies, you know what happens either to the band of frequency or to the handful of collection of frequencies. And technically, so see here how this it start from 0. There might be initial oscillations to the steady state that is not characterized. Okay, initially it might like come here like during different paths. That is not characterized in frequency response at all. Steady state, it's going to be this. This is that steady state again. So now if you do a shear experiment, if I tell you sigma is sinusoidal, right? Your strain is also going to be sinusoidal. Okay, and your epsilon, this Young's modulus will be now function of omega. Technically, this is sinusoidal, so sigma of omega at what frequency? If I tell you the sigma, I can tell you the strain using this. We have been doing this for, let's say, voltage, so function of at a given frequency. Say you had impedance, right? Then you have this I. This is a function of it. It could also be, doesn't have to be voltage and current. This is in those cases that there's impedance. You could also do, let's say, input voltage. It goes through a system, okay, h of j omega. This becomes output voltage. It could also be, so this is applicable to any system. You could have an input current. It goes through a system of j omega. You can get an output voltage. Input current, it could be like output could be current of interest, output could be even voltage of interest. Okay, things do change. We have seen this example. Impedance is one example of a transfer function. Okay, in general, this is for any system. By frequency response is a very simple example. If the amplitude changes, the phase changes. And now comes a question, sir. You are saying steady state response. What is the steady state response? Can you also differentiate that? Okay. So for that, we'll have to solve a different problem.